Hi, my name is Sam Wales, and I'm doing my presentation with Adam Egbert, and we're going to be presenting on heat engines and then taking that on into refrigerators. So jumping right in, I'm going to be discussing heat engines, and Adam will be doing refrigerators. So 4.1 in the book is heat engines, and we have a couple different pictures here to start off with that are different heat engines. So you have the Hogwarts Express, that is a heat engine. Um, this F1 car is also a heat engine, and so is this jet. Um, and then ultimately, we'll be diving into the Carnot cycle, which is what we have here. So, a heat engine is a device that absorbs heat and converts part of that energy into work, as you see. There's a couple different kinds of heat engines. The two main types of heat engines are going to be your steam turbine and your combustion engines. So the steam turbine is going to be based off of steam to drive a turbine. So essentially they're using heat to generate steam, which then powers the turbine. Combustion engines, which we will talk a little bit more about, are your practical car engine, uh, or your plane engine, boat engine, anything like that. So one of the major drawbacks about heat engines is that only part of the energy is absorbed as heat and can be converted into work. So I don't know if any of you are familiar with Dr. Sheehan's work. This is pretty much the second law, and this is what Dr. Sheehan is trying to break ultimately. Um, so in heat engines, in this case, entropy is the enemy. So an increase in entropy, as we have learned, will take you from a highly ordered state to a more disordered state, which naturally means that there's going to be some excess heat or waste heat that is associated with the process, and therefore it's not going to be completely efficient ever. So the heat absorbed by an engine comes from a place called the hot reservoir, while the waste heat is dumped into the cold reservoir. So in this diagram you see here that there's some heat source powering the heat engine, which is converting some of that to work. Depending on the efficiency of the system, which we'll get into here a little bit later in the presentation, this can change. The rest of that is diverted into the cold reservoir. So that's this area here. So that's going to be any excess heat that you have left over, and this is pretty much your losses, your cost, if you will, where any waste heat is directed. So in this case, this could be the environment, and usually is the environment around a heat source. Alright, so kind of jumping into the efficiency as I had mentioned, the benefit of operating a heat engine is the work produced, as we mentioned, and we're going to call that W, because that's what the book uses. The cost of the operation is the heat absorbed. So I couldn't figure out how to do Q sub H, so I'm going to use Q parentheses H. So any of my work you see in here for heat absorbed will be Q parentheses H. So this is an equation the book provides for efficiency. We're pretty much using that to determine the benefit-cost ratio of the system. So obviously we want the system to be as efficient as possible, and the way we looked at that is just your basic ratio work over your heat absorbed, which makes sense. Okay, so obviously that is in the most ideal system, but we have to start taking into account the laws of thermodynamics. So we're going to be looking mainly at the first and second law of thermo. Since the state of the engine must be unchanged at the end of the cycle, the energy it absorbs must be equal to the energy it expels. And this is pretty much our notation of that. So we have QH, which is our heat absorbed, and then QC here. So QC is going to be QC plus W is going to be the work plus the system at the end. So undergoing normalization under the first law of thermodynamics, we generate a new equation for our efficiency. And this is essentially more or less a normalization, so that we'll never get any efficiency that is greater than 1. So what we end up having is that E is equal to 1 minus QC over QH. So we're trying to get into what that ratio will most likely be, and that will ultimately lead us into the Carnot cycle. But right now, after the first law of thermodynamics, this is our equation for efficiency right here. But we have to take into account second law of thermodynamics as well. So this is going to add in a couple different changes. So after including the first law, we also have to take into account the total entropy of the engine plus its surroundings can increase but not decrease. So in other words, the entropy it expels must be at least as much as the entropy it absorbs. And this is essentially what these equations are saying. So we've got our hot and cold reservoirs here, and then we have our heat lost. So these are essentially the same equations. They've just been rearranged a little bit. Now we're going to use these and plug that back into the equation for efficiency to get this. So after the second law is done with it, we're going to end up getting this equation for efficiency. So E must always be less than or equal to 1 minus Tc over Th. Excuse me. So essentially, what that is saying is that we can never have an efficiency greater than 1, which we had known. And then that essentially is the ratio for what our efficiency will be. So let's say, for example, we have a temperature in the hot reservoir of about 500 Kelvin, and we have a temperature in the cold reservoir of about 300 Kelvin. Plugging that into the difficult math-intensive equation above, we end up seeing that our efficiency is roughly 40%. It's important to note that efficiencies really range. So for some engines, it can be a lot less, and then as we get into the Carnot cycle, we'll actually see a maximized efficiency. Unfortunately, it actually is very not very useful, however. So as I had kind of alluded to earlier in the presentation, the Carnot cycle is the ideal heat engine. So what this is essentially telling us, or not essentially telling us, but it gives us an idea that this is a four-step process that would be the ideal engine. So as I mentioned, it goes through 4 steps, undergoing either isothermal or adiabatic processes. So this is your first process right here from A to B, and this is deemed isothermal expansion. So what happens here is that the temperature is constant as it's expanding, and then we hit adiabatic expansion. So this is where we're actually, if we're in a 4-stroke system here, or a 2-stroke system rather, I'm sorry, this is where we've hit our maximum area and our volume has pretty much reached this peak here, VC. So at VC, we then flip back and undergo a negative volume change, slightly increasing in pressure in isothermal compression. So again, temperature is the same as we undergo compression. And actually, I think I might have gotten that backwards, but anyway, continuing on, we're undergoing compression from C to D, and then we have this spike in pressure as we move from D to A. So this is the 4th step, and I have a little animation that I found to show you guys coming up later, but this is pretty much the process in a nutshell. So again, we have an expansion, so we're starting off in a compressed state. connected to the heat reservoir. We're going to then expand isothermally, um, ultimately coming to what we know as point C, which is the full expansion state, then connected to the cold reservoir. At that point, there is a compression driven by the system, which then switches the system back over to the heat reservoir, and we restart the cycle. And this circular motion, this force that's created by this, is what drives the engine. So here's that GIF I was talking about. I have to keep clicking it to keep it working. But it's pretty much showing the same thing. So we go through an isothermal stage into the adiabatic compression to our T cold. And then we isothermal compression, and then another adiabatic stage to our original point. And this area will give you your max work as well. So just another couple times looking at this. So if you're looking at the diagram here, you can see that most of the heat is gone at this point because we're connected to the cold reservoir. We get that hot red expansion right there, and then we undergo compression again as that heat dissipates. So unfortunately, although the Carnot cycle is extremely efficient, it is extremely impractical for everyday use. So I just want to throw a picture up here of Carnot to pay homage. And something about this picture seems inefficient to me. I don't know if gas is the best choice for this gentleman. He looks like he has a mullet, so I guess the apple doesn't fall far from the tree there. And that pretty much sums up heat engines. And again, these are the most basic, ideal heat engines that we've talked about. So we've covered really the basics so far. So what is a heat engine and what are we looking for? So we talked about the hot reservoir and the cold reservoir, as well as the engine and a couple different engines that this process is applicable to. We talked about the efficiency and how we find the efficiency, which is really the main portion of this chapter, or of this section rather. And then we talked about the Carnot cycle, so the ideal cycle and what that looks like. From here, Adam is going to start talking about refrigeration. So I'll let Adam get into that, but essentially a refrigerator is going to be the same process, but in reverse. So we're actually desiring to cool something down. So instead of using heat to get work, we're going to use work to get rid of heat, if that makes sense. So that concludes my part of the presentation, and I'm now going to hand it over to Adam.
All right. Sam just finished up section 4.1, which talks about the heat engine. I'm going to talk to you guys about how the basic theory behind refrigerators and how simple refrigerators work. So refrigeration is basically the heat engine, but in reverse. So whereas energy goes from a high temperature source into a sink and you extract work from the energy moving through the engine, we actually have to put work into the refrigerator so that we can move heat from our cold body into our hot body. So the reverse of a heat engine. So the efficiency of a refrigerator is called the coefficient of performance, or COP. That's just so it doesn't get confused with a heat engine. But again, it's the same model as the heat engine. It's just the benefit we get out of our system over the cost, which is the work we have to put into our system. So the benefit is the heat that leaves our cold reservoir, and that's going to be divided by the work that's put into our refrigerator. So using the first law of thermodynamics, which says that the work you get to put in or you get out of a heat engine is equal to the difference in energies between your hot and cold reservoirs. So if we substitute that in for this work, we obtain this equation where our COP is equal to our energy stored in the cold reservoir over the energy of our hot minus the energy of our cold. And then if we divide this whole equation by the energy in our cold reservoir, we end up with 1 over QH over QC minus 1. It gives us basically our efficiency. So the second law says that entropy has to increase. So the energy or the entropy gained by the hot reservoir has to be equal to or greater than the entropy lost by the cold reservoir. So we have this inequality. So if we plug this inequality on the right side here back in for the second part of this equation, then we end up with our final inequality. So again, we just do a little bit of algebra, multiply this thing by the temperature in our cold reservoir, and we get a nice inequality that gives us the efficiency of our system given in just the temperatures of each reservoir. So this gives us an upper limit on our COP. So as you can see from this equation though, the closer you have your two reservoirs, the more efficient your system is going to be. So here is just a lightly worked out example. Let's say our temperature of our freezer was 260 degrees Kelvin, and the temperature of outside is just going to be 300 degrees Kelvin. So we see with this simple equation, we give a max efficiency of 6.5. So what this tells us is that for every 1 joule that we get, that the freezer uses, that draws from our wall outlet, it can remove 6.5 joules from the freezer. So it's pretty efficient. But if you just have a fridge, let's say that's at 280 Kelvin, we get like a much more efficient thing because of temperatures being closer. So the maximum efficiency that can be attained by a refrigerator is defined by the Carnot cycle, except which is determined from a heat engine, but again, we're going to use it in reverse. So whereas normally the work done is extracted, the area of this is going to be the work inputted. And instead of going from 1 to 2 to 3 to 4 and then moving heat from the hot reservoir into the cold reservoir, we're going to move the energy from the cold reservoir into the hot reservoir. So again, we need to put work into it, and we move from 4 to 3 to 2 to 1. The process is in reverse. So on this graph, it would be going counterclockwise, whereas for a heat engine, it goes clockwise. Thanks for watching, everyone. Please feel free to ask us questions. Thanks for listening.